Okay, this will be brief. I just wanted to show you a couple of examples of how to solve systems of nonlinear inequalities. We'll start out with something pretty simple. Right here you have 3x plus y is less than 4. So what we have to do is we have to graph its boundary, which would be the equation 3x plus y equal 4. So to graph that boundary, you know how to do this. I mean, basically you can use the x and y intercepts if you like. If x is 0, y is 4, so it would go through down here, you know, it looks like right there. And then when y is 0, x would be 4/3, so that would be a little more than 1. So down here it would be right in here, right there. And then you draw the boundary, and of course the boundary is broken, see, because I don't have an equal to, I just have the less than. And then you have to decide which side of the line to shade, which we covered this before. You can see that the point 0, 0 is below the line, and if you plug 0, 0 into this inequality, you get 0 is less than 4, which is a true statement. So you can see I've shaded everything below the line, same side of the line as 0, 0 is on. Now, for the other inequality, its boundary is the parabola y equal x squared minus 2. Well, that's just the standard parabola y equal x squared, except it's shifted down 2 units. So notice the vertex is below the x-axis. So here's the parabola. And now again you can test 0, 0. Now basically 0, 0 here is above the parabola. If you go straight down, you'll see the parabola is below that point. So if we plug 0, 0 in, let's see, we get 0 is greater than or equal to -2. Well, 0 is greater than or equal to -2, so the 0, 0 gives me a true statement. So I shade everything above the parabola, which basically turns out to be everything inside, but I don't like to say it that way. We're shading everything above the parabola here. And then when you look for the intersection of these two shaded regions, let me try to draw it for you here. You just follow the parabola down here and around, and then you follow this dashed line. And so the solution is what's inside that red boundary there that I've drawn for you. And that's basically it. That darkest region in there is the solution. Okay, here's the other one. Let's start out with this one. The boundary for this one would be x squared plus y squared equals 1. Now that's just going to be a little bitty circle. It's going to be a circle with radius 1. So you can see down here I drew the circle. See if I can highlight it a little better for you. Let's see, right there. So you can see I drew a circle right there. And then notice that 0, 0 is inside the circle. So if you plug 0, 0 into this inequality, you get 0 plus 0 is greater than or equal to 1, which says 0 is greater than or equal to 1. So that's false. So basically what I had to do to graph this is I had to shade everything outside the circle. So basically you've got to graph everything outside the circle. And so that's basically it's actually that kind of pinkish looking region. You can't see the whole region because it's kind of overlapping with some others. But that's what I graphed there. But then let's go ahead and drop down to this one first, because this will help. I think it'll help to do this one next. So this one, the boundary is x squared plus y squared equals 25. Well, that's another circle that's centered at 0, 0, but its radius is 5. So if you'll notice here, I drew this bigger circle here, right here. Let's see if I can fit it on here. Something like this, anyway. Okay, there you go. All right, so now that circle is there, and then when I test 0, 0, which is inside the circle, I get a true statement. I get 0 is less than or equal to 25. So basically, now I'm tied. Let's get rid of these marks. Now I'm tied to just this disc or washer, if you please, that's right here, this purple washer that's going around. Okay, so try to take away that green stuff for just a minute and just think of this purple washer that's inside the big circle but outside the little circle. Now the last thing I have to do is I have to graph the boundary for this, which would be y equal absolute value of x, which you know how to do. But this has to be graphed with a broken line. So you can see when I graphed y equal absolute value of x here, I used a broken line. And then I can't test 0, 0 because that was on the circle. But what if you just said, how about 0, 5? How about this point right here, 0, 5? So let's let x be 0 and y be 5 and see what happens. Well, that would give me 5 here and 0 here. So that would mean 5 is greater than 0, which is a true statement. So that would mean that I shade everything that's, since the point 0, 5 is above this graph, then you shade everything above it. So basically, you're going to get, you know, all of this. Well, before I dip down in there and mess up the picture, let's think about what that's going to give me. What all that's going to, that overlap, where's that going to overlap with that washer? Well, it's going to overlap. Let me get some of this stuff out of here so I can finish the picture. So it's actually going to overlap out to here, and then also out to here. There's the broken line, and then it's going to follow that circle. So you're going to kind of get kind of a wedge there with no boundaries here and here. So that's the region there. So a little bit tricky, but you can eventually come up with that dark region that represents the graph of where those three inequalities intersect. Okay, I thought I'd throw this one at you to give you some logs and some exponentials. So the boundary for this one would be y equal natural log of x. Okay, well that is actually going to be this piece right here. Hang on just. Okay, so this is y equal natural log of x. That's what that looks like. And we want to shade where y is greater than that. So let's see. It doesn't. Here's the point 0, 0 right here. So now 0, 0 is above it. So let's say, well, I can't plug 0 in because of the log. But how about we plug in this point? How about the point 1, 2? We can plug that in, can't we? So if x is 1, natural log of 1 would be 0. And if y is 2, so certainly 0 is less than or equal to 2. So that's a true statement. So you shade everything above this graph. Okay, now how about y equal 3 to the x? Well, that's an exponential function. And here it goes right through here. I don't want to draw over it, but there you can see it going up through there, y equal 3 to the x. Okay, so there's y equal 3 to the x. Now that one I can test 0, 0. So let's put the point 0, 0 in and see what happens. Well, if I put 0 in for y, I get 0. And if I put 0 in for x, I get 1. So I get the statement 0 is less than or equal to 1, which is true. So that means I shade everything below. So right now I've got everything above the log function and everything below the exponential function. But then I've got to keep my graph between these two lines, x equal 1. And you see this dotted line right here? That's x equal 1. And then this dotted line right here is x equal 2. So I've got to keep the graph between those two lines. So it's everything below this graph, above this graph, but between these two lines. So basically, let me see if I can kind of trace it here. It's there, and then you go down here, and then you follow the log function, and then it goes back up. And so it's everything that's in that boundary right there. So that would be the region. So that would be the solution to that. And so that's how you graph systems of nonlinear inequalities. Just like graphing systems of linear inequalities, the graphs are just not linear.